Dear students, we'll start a new chapter in abstract algebra which deals with permutations and permutation groups. Already we have learned basic definitions of groups and subgroups, some important theorems in the last several videos, and this is precisely a very important chapter which is having its own significance in abstract algebra and group theory. So let's see what are the preliminary ideas dealing with permutation groups. So first we'll define what are permutations and see how permutations can be collected and formed into a group. Okay, let's have some definitions first. A permutation is a bijective function from a set A onto itself. That means if you have a function as f, the domain must be A and the codomain must be A. It's a function from A to A which is 1, 1 and on to. So any bijective function from a set A onto itself is defined as a permutation. I'll say later, you might have learned permutations in your plus 2 classes in a different way, but that is a particular case of this function that we will see later. Anyhow, some examples, one or two examples I'll be giving you as examples of permutations. First one, every identity function from a set to itself is a permutation. Identity function means you take a from small a from that capital A, then identity function of that A will be the same A. That means domain is same as codomain, means that A will be present in codomain also. So every element is mapped onto itself. That's what we call it as identity function. So such identity functions will be 1, 1 as well as onto. Therefore, identity function is always a permutation. Second one, consider the set of real numbers. Consider the set of real numbers R and take a function f from R to R. Define f of x is equal to x plus 1. That means every number is added by 1 as to get its image. Then you can prove that this is a function from well-defined function from R to R, which is 1, 1 as well as on to. You can prove that it's a permutation. So you have to prove it actually. Means you have to first prove that it's a well-defined function. Second, you have to prove that it's 1, 1. Third one, you have to prove that it's onto. Okay, that's an exercise for you. Homework, more homework. Check whether the following functions are permutations or not. First one, f1 from R to R defined by f1 of x is equal to x square. If x is mapped onto its square, what will happen to that function from set of real numbers to real numbers? Is it a permutation on R? That's a question. Second one, I change the domain of f2 as positive real. This is positive real numbers, 0 actually. This can be shortened as interval 0, infinity. So set of all non-negative real numbers to itself, defined by f2x is equal to x square. The same previous function. Previous function is from R to R. Now I have just taken the subset of R, and I'm defining the same function f2x is equal to x square. See whether that kind of thing is a permutation from R non-negative real numbers to non-negative real numbers. Now the third one, set of positive real numbers to positive real numbers. That is f3. Defined like this, x goes to e raised to x. Is it a permutation on R plus? That's a question. So these three questions along with the first one can be taken as a homework. Now we'll come to an important concept called group of permutations. That means already we are now familiar with the notion of permutation. So you take so many permutations, and can we collect all those permutations on a particular set A and make that collection of permutation as a group? That's a question. Let A be a non-empty set. Is any non-empty set, maybe a set of numbers, set of individuals, set of books, whatever it is. an abstract set. It's an be a non-empty set. Let SA, carefully observe the notation, S suffix A denotes a set of all permutations on A. Then we'll be proving that this SA is a group under the binary operation composition of functions. Composition of functions you may be familiar with. F and G are two functions, means F composition of G will be defined with the domain of G to the codomain of F. Okay, that's familiar to you, which is to be learned in previous classes. Anyhow, so what we are going to do, we will be proving that this SA under the binary operation composition is a group. That's what we will do. Let us denote the composition of two permutations by this symbol, sigma O T. So later I will be simply writing it as sigma T. It means that in between the operation is composition. For the time being, let me specifically take this as O, sigma O T. Now in this video I will be proving that whenever you choose two permutations, the composition of that is again a permutation. This is so that's composition of two permutation is again a permutation. That's what we mean by closure property. Closure property means if you have a binary operation star, A star B must be again to the concerned group. Here the group is SA. Okay, so first we'll prove that this composition is a binary operation. So for that, it is not the complete proof of calling it as a proof. This is only a proof for proving that this composition operation is a binary operation. So take two permutations, sigma from A to A and tau from A to A, belonging to SA. Then I will be proving that this function, sigma composition of T from A to A, since A means sigma composition of A, the tau will be from A to A. So in order to prove that this is this belongs to sigma composition T belongs to SA, what we have to prove that sigma composition T is well-defined function first we have to prove. So to prove a function is well-defined, I have already told you how to check it. You take two equal elements from the domain A, then necessarily as tau is a function, image of A1 and image of A2 must be the same under tau, as tau is already a function. Then you apply sigma on both sides. Sigma of tau of A1 is equal to sigma of, because these are equal means sigma is a well-defined function, therefore the image must be same. Sigma of tau of A1 is equal to sigma of tau of A2 means it is, we can write this as sigma composition of T of A1 is equal to sigma composition of T equal to A2. So what we have done, we have chosen two equal things. The images are also equal. That's what we have got. So sigma composition T is well defined. Now to prove that it's a bijective function, first we will prove that it is onto. So onto means you have to take something from the codomain. So I have chosen C from the codomain. Why it is C, I'll tell you later. Anything can be taken, but C, you can see how the proof, when the proof goes on, you will see why it is taken as C. So let C belongs to A. A is the codomain of this sigma composition of T. Then C belongs to A, there exists B belongs to A such that sigma of B is equal to C. Sigma is already onto, therefore you can find a B which carries B onto C by sigma. Now this is equation number 1. Now B is now in A. B is now in A implies there exists A belongs to A such that tau of A is equal to, because tau is onto. We are applying the property of onto property of sigma first, then that of tau later. So now go back to equation 1. This B can be replaced by tau of A. Therefore, sigma of tau of A is equal to C. Sigma of tau of A equal to C means sigma composition of tau of A. So whenever you take any element C from the codomain, there is an A which carries that A to C under the sigma composition T. Therefore, sigma composition T is onto. Now to prove that sigma is 1, sigma composition T is 1, how to prove a function is 1, you take equality for the images. So let sigma composition T of A1 is equal to sigma composition T of A2. By definition of composition, this is the second step. Now these are equal means tau of A1 must be equal to tau of A2 because sigma is already 1, 1. So we are applying the 1, 1 property of sigma. Now tau of A1 is equal to tau of A2 implies A1 is equal to A2 because tau is 1, 1. So what we have started with? We have started with equality of this, and finally we got equality of this. That's I have written here. So whenever images are equal, pre-images are equal, therefore sigma conversion t is 1, 1. So what we have got now, sigma conversion t is a function which is well defined and which is 1, 1 as well as onto the which is bijective function. So every function which is bijective is from A to A is a permutation, therefore sigma conversion t belongs to SA. Therefore closure property holds good. So with this we end this video. We'll have